In this section, we have a few properties of logarithms to go through. I have listed some 7 properties of logarithms here. The first one says that for any valid base a, log of 1 in any base is 0. And by the way, most of these you can prove by just simply rewriting them in the exponential form. So for example, if I read log 1 base a is 0, if I rewrite it as a to 0 equals 1, and we can see that any non-zero base a, and we have set that straight here, a cannot be 1 and a has to be positive. So it cannot be 0. Therefore, for any valid base a to 0 power, using properties of exponents, that is 1. Okay, so that one is proved so easily. This one is done the same way, and likewise this one is done the same way also. And this one even you can do it the same way. Write it as a to the r equal to the argument of a log, which is a to the r, and that proves this one. So very simple to prove these. The next 3 properties, first one is the product rule, or product property of logarithms, that reads a log of a product. And notice, by the way, the product here happens in the argument of the log. Okay, so I don't have something like this per se. I don't have log m times log n. That does not equal to log of m plus log of n. Okay, so I want to emphasize that because that is not true. So if the product is in the argument of a log, we can write that as sum of 2 logs. So oftentimes we say log of a product is sum of the logs. The one below it says log of a quotient, division. Log of a quotient is difference of logs. And again, the incorrect way to use this one is if you say log of m over log n would equal to log m minus log n. Again, that is not true. Okay, so please be aware of the proper use of these properties. And this one, if you have a power on the argument of a log, we can move the power as a factor in front of a log. That means it becomes r times log m in any base a. Okay. Now we have another property here which applies with natural logs, which is quite handy. And there's this one, that a to the r can be written as e to the r natural log of a. This form, this property, we tend to use this somewhat in second semester calculus. These properties are used, this one in particular. So to show this one is true, you can actually cite this property of logarithms. This one, a to the log base a of m is m. So we know that a to the log base a of m is m. We know that, correct, from the earlier property. So if you let the base a be actually e, the base of the natural log, so this is now the log base e, and then the argument, I'm going to let it be a to the r. Well, here's your a, and this is your m. So this is going to be a to the r, correct? Do we know that from the property? Now, the log itself, we can use this property to bring the exponent that is on the argument of the log, namely r here, in front of a log, correct? So I can write this as e to the r log base e of a, and that's a to the r. Now log base e is natural log, correct? So we can write this e to the r ln of a is equal to a to the r, and that proves this property of logarithms. Okay, so there we have that one. Now the other idea here in this section is that helps us solve logarithmic equations, actually this, that goes if m is equal to n, then log of m should equal to log of n. And remember, logarithmic function their origin were exponential functions, the work we did, right? So because exponential functions are one-to-one, so are logarithmic functions. So this property follows from the one-to-one property of logarithms. And again here, m, n, and a are positive, and a cannot be 1. Okay. The other property we have is this. Now, if log of m is equal to log of n in any valid base, then m should equal to n. In other words, the argument of the logs should be the same. Okay. And the last thing that we have is the change of base. The change of base has its own merits, but it used to be because calculators could not handle any base other than natural log and common logs. So there was a need for change of base. It has its own merits again in proving other properties and so on, but it was primarily used as means of calculating logs that had bases that were different from E or common logs. And there you go. So the change of base says if you have log m in any base, valid base a, you can write it as log m of some base in valid base b divided by log a in that same base b. Again, for both of these, a and b cannot be 1. That follows from up here. A, B, M are positive. A, B, and M are all positive. Okay. Now, because if you have to use change of base on a calculator, especially the older calculators that are not capable of handling all valid bases, we usually use, let me just note that, you typically use natural log and common logs with change of base. Natural and common logs for change of base. So for example, let's say I want to do log log 5 in base 7. So my calculator cannot handle this, so I can do this as natural log of 5 over natural log of 7 and use my calculator. Or I can choose the common log of 5 over common log of 7. Remember, if the base of the log is not there, it's presumed to be there, and it's 10. So we call that a common log. So you can do it both ways, either or. All right. Now let's take a look at just some basic examples here. Suppose I want to simplify these, find the value of the logarithm. So I have ln of e to negative 4. Well, using the properties of logs, I can bring exponent negative 4 in front of a log, and that's going to be negative 4 ln of e, and ln of e is 1. And the reason that is 1 because ln of e is log e base e, and that is 1. That was the second property we had up here, right? This one. So everything I'm doing in the example, you can refer to these properties. Okay, so I don't have to scroll up and down to visually distract you. Okay, so the answer to that is negative 4. Okay. Now, let's say another example. Suppose I want to evaluate log 2 in base 8 plus log 4 in base 8. Using product property of logarithms, I have sum of two logs, so I can write that as log of a product, 2 times 4 base 8. And that's log 8 base 8, and that is namely 1. Okay. And then we have 4 in this other example. Suppose I have 4 to the power of log 6 base 4 minus log 5 base 4. So first I'm going to handle the exponents using quotient rule. Log of 6 minus log of 5. Again, log of a difference can be written as quotient of two logs, right? So I can write it as log 6/5 base 4. And now using the other property, this one, a to the log base a of m is m, I can write the answer as just 6/5 for this one. Okay, so that's the property I used for this example. And let's take a look at another one. Suppose I have a natural log of x. This time I made a quotient, x over e to the x. And log of a quotient is going to be difference of logs, so that's ln of x minus ln of e to the x. Okay, and you can write that as ln of x minus the exponent moves in front of a log, right? So that's going to be x natural log of e, and natural log of e, because it's log base e of e, that's 1. This is 1. Therefore, the answer to this is going to be ln of x minus x. Okay, and don't combine these into 0. Those are two different terms of an expression. All right. Now, let's take a look at another one. Suppose I have, in this example, this is going to be slightly more challenging. Suppose I have log e to the log 16 base e squared, not e. If that was e, the answer would be just 16, but it's e squared. Okay, so here's a good example of change of base, where change of base comes in very handy. So there is the e, that's the base, that's the e here. Now, log 16 base e squared, I'm going to use change of base and write it as natural log of 16 over natural log of e squared. Again, using the change of base, I rewrote the exponent. All right, now natural log of 16 is whatever natural log of 16 is. That's ln of 16, and the denominator now ln of e squared, again bring 2 in front, that's 2 ln of e, which is 2 times 1, and that is 2, and divided by 2. Okay, now the 2, I can think of ln of 16 over 2 as 1/2 natural log of 16, correct? It's just like this. If I have 5 divided by 2, I can think of that as 1/2 times 5. Something that simple. So that's how I choose to rewrite this one as 1/2. I changed division to multiplication with reciprocal, is what I did. All right, now using properties of logs, I can write 1/2 ln of 16 as ln of 16 to 1/2. Again, here I'm using the property that says, let's say m to the r. Remember this one, r log m base a. Well, I'm going from right to left. Put r back in the exponent, and it becomes that. So I put 1/2 back in the exponent, and now it's ln of 16 to 1/2. Okay. Now 16 to 1/2, isn't that the square root of 16? Right? When we say 16 to 1/2, we can write it as a radical expression as the square root of 16, and that is 4. So this is e to simply natural log of 4, right? That's 16 to 1/2. And e to ln of 4 is simply 4, right? And there we have the value of this expression. So this one a little more challenging, but the other ones were not so terrible. These were quite manageable, these other ones. Alrighty, and hopefully this was a good selection of examples for you. Now let's take a look at just 2-3 more and we'll be done. So for this next example, suppose I'm given a log of a single expression. Okay, and I just want to use properties of logs, namely multiplication and division, to expand this expression. And in all of these, I'm assuming x is positive, so we don't run into issues with the argument of log becoming undefined. Okay, so let's say I want to write this as sum and difference of logs. So first I see a fraction that's going to be a numerator, which is this, minus a denominator. And my base is not written, so I'm working with the common log. Okay, so we don't have to write a all the time. This works for any base, any valid base. So I'm choosing a common log here. All right, and then the first log, I see a product that's in the form m by n. So I can write that as sum of two logs. That would be log x plus log in parentheses x plus 2. Okay, and it's important that we maintain parentheses, by the way. If I write log x plus 2, I'm just being careless here, but I mean it to be what's up there in parentheses. This is not the same as log parentheses x plus 2. The reason is because of order of operations. If I write it without parentheses, what gets executed first is log of x, and then the result 2 is added to the log. In other words, this is the same as 2 log x, which is not the same thing. With log x plus 2, first the operation occurs in the argument of the log. You do x plus 2, then take the log of it. So the key idea here is to maintain parentheses. It's just so it's written correctly. The next log, I can bring the 2 in front of a log, right? The exponent on the argument appears as a factor in front of a log. And there we have that one. All right, and that's what we wanted to do. Write it as sum. Here's the sum and difference of individual logs, and we did. Now sometimes we want to go the opposite route. So let's say I have 3 log u in some base, make it 4, 5, whatever, and then suppose I have 4 times log v in base 5. So I can write this as log of u cubed and then plus log of v to the 4th, right? Again, the coefficients move to the exponents in the argument of the log. And once we have this, we're going to multiply. So log of sum of the logs becomes log of a product. So it's u cubed v 4th and then base 5. And there we have a single logarithm. Okay. This would be ideal. Single logs is when we solve logarithmic equation. It's a lot easier to do it as a single log than a log that's spread out. Excuse me. Okay, so let's take a look at this maybe last example. In this last example, suppose I have natural log of x over x plus 1 plus natural log of x plus 1 over x. Okay, so let's throw in another log in there, negative natural log of x squared minus 1. All right. Now let's write this as log of a single expression and simplify it if possible. The sum of the logs, see, sum turns into a product, difference turns into a quotient. So first I'm going to do the sum. Remember, order of operation, I'm doing left to right because I have addition, subtraction. So I'm doing it from left to right. I'm going to do the addition first. Log of m plus log n becomes log mn. That's what I'm going to do. And then that gets divided by x squared minus 1. All right, so here it goes. It's going to be x over x plus 1 times x plus 1 over x, right? That's natural log of that. Let me put one more step in here. And now I can write this as log of a quotient. Now before I do, I'm going to go ahead and cancel these x's out just to simplify them. And what else? Oh, the x plus 1s. The x plus 1s cancel too, don't they? Wow, isn't that something? Well, that was easy. It worked better than I thought. So this is just going to be natural log of 1 minus ln of x squared minus 1. Well, ln of 1 is 0. So I have negative natural log of x squared minus 1, right? So how can I work this one? Okay, well, this is just the way it is. One thing I could do is I can think of negative as negative 1 ln of x squared minus 1. Put negative 1 in the exponent. So it's going to be ln of x squared minus 1 to negative 1. and use negative exponent rule to write it as 1 over x squared minus 1. And there you go. All right, so that's how this one works out. Now, if I made it to where this wouldn't happen so easily, then it will get a little more exciting. Maybe let me try that. Maybe instead of x over x plus 1, I'm going to go x minus 1. So things don't multiply to 1 in the first step. I still want to have the product rule followed by the quotient rule though. ln of x squared minus 1. And now let's do the product rule. When we do, we get ln of first expression times the second expression minus the last expression. Okay, so we have that. Now let's multiply like I did before. This time the x's cancel, but the x plus 1 does not cancel, which is good. So this becomes ln of x plus 1 over x minus 1 minus natural log of x squared minus 1. Now I can form my quotient, right? So when I do the quotient, this is ln of m minus ln of n. I'm going to go m over n, right? There, in that form. So that's going to be natural log of the numerator is going to be x plus 1 over x minus 1 divided by x squared minus 1. This is a little bit more exciting than the one above, which this can be now written as an ln of x plus 1 over the x minus 1 moves to the denominator times x squared minus 1. Or you can think of it as x plus 1 over x minus 1 divided by x squared minus 1. Invert and multiply the denominator. This becomes 1 over x squared minus 1. The next step from that is exactly up here. Okay, if you invert and multiply. Now, however you think of it, I can rewrite x squared minus 1. I recognize that as difference of two squares. So this is going to be x plus 1 in the numerator. In the denominator, I have x minus 1 times x plus 1. That's the factored form of x squared minus 1. Difference of two squares. Factors as product of two conjugate binomials. Now I can cross out the common factors. So when you cross out, nothing left on in the numerator. I'm just going to put 1, so there's something there. Can't have a blank. Okay, and now this one we can rewrite this using properties of logs. This is going to be ln of 1, right, minus ln of x minus 1 squared. Because I have two factors of the binomial, I wrote it as a square. And I use the quotient rule again. ln of 1 is 0, and bring 2 in front of a log, so that's negative 2 ln of x minus 1. And there you have it. We wrote it as a single logarithm. All right. And that's all I wanted to do in this section. So we'll keep it short to under 30 minutes. And there you have it. All you want to know about properties of logarithms. All right. Thank you for watching, everyone. We're done with this video.